Hello, everyone. Thank you for joining. This is the, well, I think this is the 6th meeting of our journal club. Actually, we also have almost the same number of people as we always have. Almost, someone is trying to join. Almost 25 people. So thank you again for joining. I think there are less people from IOB today, but more people from outside. But in any case, it would be good if you can keep, some of you can keep your videos on among the students. It's okay as is now, actually. So today we are having another session in English because we have invited another person from outside Bangladesh who will be presenting his recent work. And also, actually, we have Bayesian among us as well, who was present, who actually gave the first author series presentation like 3 weeks ago. So thanks, Bayesian, again for joining. And our today's speaker is Iniyan Natarajan. He is a postdoc at jointly at Rhodes University and the South African Radio Astronomy Observatory, right? Do you have a joint appointment, Iniyan, or is it only?
No, it was always just Rhodes. I'm just, I'm based
okay. Okay, so the postdoc is at Rhodes University in Grahamstown in South Africa, but he's actually based at the South African Radio Astronomy Observatory, where I also used to work until 2019. So I was also a postdoc at South African Radio Astronomy Observatory. And this observatory is the place where things are happening related to SK. So SK, as some of you know, that is the largest radio telescope that is being built in South Africa and Australia. And this SARAO was specifically established to make this happen. So Iniyan will talk about in general, probably the importance of probability and inference in astronomy, but also with some specific examples of what he is doing. And also, I circulated his paper. So Iniyan, I was reading your paper. I haven't finished it yet, but the beginning was really interesting because you started from scratch. So So maybe it will be, So in any case, as you know, most of the students are undergrad, so probably they don't, most of them probably also did not take any like statistics course that would be helpful in this respect. But in any case, so I think it would be better for us in any case if you also explain from scratch a little bit.
Yeah, so I have some intro on how Bayesian inference is done, and then some intro on radio interferometry as well, and then I talk about how so far I've been using. I also have some examples from my PhD. So the work that was in the paper, that's only in the last few slides, but I'm starting from an introduction. So hopefully it will be useful for everyone.
Yeah, okay, then probably you can begin.
Okay. Hi, everyone. So yeah, I've been a postdoc at Rhodes University in South Africa for a few years now. I did my master's and PhD, everything at the University of Cape Town. So yeah, I've been a Cape Townian for almost a decade now. Okay, so let's go into this. So this whole idea, sometime at the start of my PhD, I mean, this is just a bit of context. Like, so a postdoc who was working at the University of Cape Town, he came to me with this nice idea about using Bayesian statistics to get information from radio data. I mean, it was immediately interesting. And then as I started working on it more and more, I realized, like, I mean, Bayesian, the Bayes theorem and the associated statistical inference methods are just like a mathematical quantification of how we make decisions in real life. And this was a very interesting aspect to me. And I've been working on this. I mean, regardless of what, I mean, for my postdoc, my focus is something else, but also I've kept this stream going in my research. So the idea is to talk about probability and inference as used in astronomy, and I'll give some examples and applications from my field, which is radio interferometry. So I'll also, I mean, after this talk, I'll give you some recommendations, the books that you can use for this. And there is a really nice book called Probability Theory, The Logic of Science by Edwin James. And that's basically what it is. It's the logic of science. It's the mathematical foundation about how we make inferences. So let's begin from the beginning. As Einstein said, the most incomprehensible thing about the universe might be that it's even understandable to us at all. We were not here when it began. We are late to the party by 13.7 billion years. So we are forced to reason backwards about how the universe works from what little we can see of it. And that it obeys any laws at all, much less those that are understandable by us, on a small planet somewhere in the corner, it might be the greatest mystery of all. And the information we possess about the universe is always incomplete. We are always limited by our senses and our location in space-time. So what we do is we build better tools to observe the world around us better. And luckily, we possess the ability to understand it in terms of models. Our brain always forms models of the universe around us. And like, what's a model? A model is just a representation of the physical world around us that becomes more or less plausible based on the results of our experiences, or in this case, consciously designed experiments or observations. And this process of inferring causes or refining your models about how the world works from data when you have incomplete information is called scientific inference. This is the basis of decision making. But there is a catch here. There are always uncertainties associated with the measurements we make. The uncertainties may be associated with the instrument or the very process being observed, or maybe our models are inadequate, and our models are almost always inadequate as we continue to refine them. So we have to somehow be able to account for these uncertainties in a robust mathematical way. And because we are doing this inverse reasoning, there's no unique mathematical solution. So we are always forced to take into account any relevant prior information while drawing inferences. Any information that you may have about how the world works should become part of the inference process, but it should be done in a mathematically consistent way. And probability theory, it's a very broad topic, but this whole umbrella is called the probability theory, provides a robust mathematical way to update one's beliefs based on empirical results. So now I'll start a bit of an introduction to Bayesian probability. So most of you would know about the classical notion of probability. It's called the frequentist notion. This measures the relative frequency of occurrence of an event given a large number of trials in the limit where n tends to infinity. So this is where you get experiments like somebody throws a dice a number of times. What is the odds that you get an even number in n number of trials? So here, the repeatability of experiments is the key concept. So you assume that an experiment can be repeated multiple times. If you can, you also repeat it multiple times, and then compute this notion of probability. And this is applicable to any problem that you can cast in terms of random variables. So you have like, let x be a random variable that describes this and this, and then each occurrence is an instance of the random variable. So this is all the basics of frequentist probability you would have learned. The Bayesian notion is slightly different, and it may not seem like a big difference when someone states the concept, but it makes all the difference in terms of its applicability. So the very definition of probability is redefined as the degree of belief one has in any proposition based on available knowledge. It's kind of the ultimate quantification of one's humility. So here, information is the key concept. What information you already have, that is called the prior information, and what information you obtained from the experiment, these together decide how much you choose to believe in a certain proposition. So because of this, it's more generic. it can handle propositions of the form like, will it rain tomorrow? These are the kind of everyday questions for which different people have different answers. And different people have different levels of belief in the same questions. Like I can ask somebody, I can ask in this group whether it will rain tomorrow, and each one will have a different degree of belief. So this is designed to handle such questions. And this is the mathematical statement of Bayes' theorem. Some of you might have seen. Given two propositions A and B, the probability of A given B is what you see on the right-hand side. So have you, can I ask a question? Have you done conditional probabilities?
Yes, sir.
Yes.
Yeah, okay. Yeah, and no, please don't call me sir. You can just call me Iniyan.
Because they are used to calling, because unfortunately people call me sir here. Well, that's the one.
Yeah, no, please call me Iniyan. I know. When I meet my own professors, I still call them sir. So, yeah.
Yeah. Where is the picture? So, I probably missed that. Where is the picture from? Do you know? This photograph, I mean.
So I took it from Wikipedia, but I think this is on the on the entrance or somewhere of like one of the HP offices currently. I think maybe they're researching or something. It's on Wikipedia. I didn't read it properly.
Mm-hmm.
Yeah. So the P of A is the probability that the statement A is true, and like here proposition or statement are kind of similar. I'll use them interchangeably. And P of B is probability that B is true, and probability that A is true given that B is true. That's the conditional probability statement. So this you can derive by like the basic law. There is a rule called product rule in conditional probability. So what you see in the denominator on the right-hand side is actually on the left-hand side. That's called the product rule. And so because scientific problems are often are better cast in this way, that is P of A given B, that is what we normally want to know. And I'll give some examples for this. So yeah, so let's see this in a bit more detail with some examples. So P of A is the prior in the Bayesian jargon. And this is our belief in a model before we collect the data. And please interrupt me if you have any questions. And the other term in the numerator, probability of B given A, is the likelihood. So cast in terms of two propositions, there's not much of a difference between A given B and B given A. But here, A is what like represents our model, and B is what the information we processed before. So in that sense, P of A given B and P of B given A, they don't perform the same function mathematically. So P of B given A is called the likelihood. It just tells us how likely is the data given the model. It's a function of the model itself. So if you think of A as a set of parameters that describe a model, then P of B given A is your classical probabilistic analysis. That's what you normally do. That's why you do all your like chi-squared reduction, computation of likelihood functions, and these things. They're all encompassed in P of B given A. That's your traditional statistical analysis. And P of A given B is the posterior, which is the modified belief after you take the data into account. So the new term in Bayesian inference is P of A that you see on the top. That multiplied by your classical frequentist analysis gives you your posterior belief. So it's basically your prior beliefs, you're openly acknowledging that your prior beliefs are modifying the degree to which you choose to believe the data. And P of B is called the evidence. It's just a normalization constant that's independent of model. We don't really need to go into the details here. but I'm happy to talk about it later. So, okay, let's look at an example from cricket. So let's say there are two different people, and I tell them, I give them a statement. So the statement A is this: Bangladesh will win this ODI today. How much do you believe that they will win? And then like two people might have different probabilities. You see it on the diagram here. So there's a green person and a red person, and they might have different prior beliefs on this. Let's say one person thinks, well, I mean, I don't think they'll win. I only have a 20% belief that they'll win today. Another person is very confident. They say, well, I'm 80% sure that they'll win today. And then, but they don't have any information. They're not watching TV. We have locked them in a room, let's say. And then I'm just telling them, okay, the match has already started. Most of the match is done. I'm giving you some extra information, which is they need 30 runs from 30 balls. That is proposition B. Now, given this, does your belief change? Well, you might think about it and say, oh, 30 runs from 30 balls. Now, with the person who said 20%, they might be like, I don't know, maybe they can do it because these said 30 runs from 30 balls is easy. So maybe I believe 40% that they will win today. But the person who is like 80%, they're like, 30 runs, 30 balls is maybe not worthy of 80% confidence. I'm only 70% confident now. And then you can kind of chain more statements to this, and the posterior. Now their posterior is their modified belief. That will become the prior for the next level of inference. So I can give them a next statement. Well, I can tell you that there are only 3 wickets remaining. How does your belief change now? And then I'm saying, okay, they're playing away. Maybe they're playing in England, and then the conditions are not good for, say, subcontinent cricketers. Or maybe they're playing at home, in which case England is at a disadvantage. So all of this information becomes like the prior information, because this particular instance that corresponds to A hasn't happened yet. You try to modify your belief that they will win based on what has happened in the past. Maybe you go to some cricket website, you do an analysis, you look at like how many times have they won when there were only 3 wickets remaining? How many times have they won when it was an away match? You do something like some kind of analysis. But this is, of course, you don't go and do a mathematical analysis of these things, but this is the kind of thing that you do in your head as your belief modifies as the match progresses. So, and this diagram, it's a very important diagram, and this is what, this shows how the beliefs of 2 people will converge given enough data. 2 people might have different beliefs, and then you see the blue here in diagram B is the likelihood. That is the analysis you've done based on the data. And that and your belief put together will modify your posteriors. So after like one round of this, the priors of 2 people have converged a bit, the green and red. And D is it's a simulation that the author did, and after 100 trials or something, this is what happens. So as long as you are not stubborn, and this is the thing about the priors, as long as the prior is not 0 or 1, as long as you're willing to admit that there is a small possibility that your prior belief might be wrong, as long as you're willing to do that, then maybe you'll need a lot of data to convince you that your model needs to be modified, but you'll get there, as long as you do the data analysis honestly. And of course, there are all these caveats, but this is as much as we can quantify the decision-making process. And this applies to all kinds of scientific problems. I just took cricket, but yeah, applies to everything. So you can do this kind of statistical inference at 2 different levels. One is, so let's say here, the theta that you see is a set of parameters that describe a model. And M is the model, D is the data, and any and all relevant external information is encompassed by I. So the first level at which you do Bayesian inference is a simple parameter estimation. You have some data and you want to fit a straight line to it. So you have two parameters, and those two parameters are given by theta here. So what is the value of theta, that is those two parameters, given the data and the model, which is your belief that the straight line is the right model to fit this data, and then any other relevant information is what is the physical phenomena that you're trying to analyze, etc. And then,
Can I just ask a question?
yeah.
What would be the difference here between I and D?
So generally, D here is like the result, the data that you collected based on like a specifically designed experiment. Let's say, oh, you did a certain observation of a star or a galaxy, or you did some experiment in the physics lab to measure a certain quantity, and that's D. Well, I could be something like, let's say you're doing some experiment in a physics lab, and maybe it's a very hot day today, and you know that whatever thing that you use to measure might expand or contract in the heat. So that might be a source of systematic error, like all external information. So D is something that's very quantifiable. It's the thing on which you perform your analysis. M is your belief, that is that you think that this quantity can be described by this. Like, for example, if you have a collection of data points, you know there is a sum. So you have X and Y, an independent and a dependent variable, and you have collected some data, and you have a scattered plot, and you think a straight line is the best thing to fit that data. So the parameters slope and intercept of the straight line are given by M, right? That's your model. Because, for example, when you go to the next level of inference, okay, I'll come to that later. But so that's your model, and the inference is that, for example, you're looking at the extra information I is something like this could be the relationship between the mass and luminosity of stars, something, and we know that maybe they should follow a certain relationship given by a certain curve.
Can I add some? Tana, can I ask? So is like the error of the, for example, if I'm doing an observation, is the error of the telescope also part of I? The instrument, or is it?
No, naturally that will be a part of your likelihood. Like, so your uncertainties, let me put it this way, assuming like simple Gaussian likelihood, something like that, any random uncertainties in your measurement will be taken care of by the likelihood function. That is actually the analysis of the data. But certain systematic errors that you may not have taken into account of, like, for example, on that day, that scale was, you know that the scale would have contracted by 1 millimeter or something like that, depending on the weather. So that is a source of systematic error. So that, for example, you might have to add 1 millimeter to all the values that you measured on that day, something like that. So yeah, if your likelihood doesn't take into account of certain source of systematic error, then they will be part of the extra information.
Okay.
Yeah. I don't know whether I explained it clearly, but yeah, if you still have any doubts.
Yeah, now. Yeah.
Yeah. Okay. Yeah. So the second level is model selection. So this is like, let's go back to the same example where you have some relationship between X and Y, and well, you tried fitting a straight line, and normally we'll probably try and see, okay, maybe a straight line doesn't fit very well. We'll normally compute something like a reduced chi-squared or something. You see that, well, the reduced chi-squared is like 4.5 for a straight line. Well, maybe I should try and fit a parabola and see what the reduced chi-squared for that is, right? And this is the kind of analysis that will change. So here you start comparing two different models, like the parabola. The relationship between the parameters of a parabola will be different from that of the straight line. So at a second level, you do a parameter estimation like analysis for each of your models, and then you compare the evidences, like the postings you got for the two models, and that's called model selection. So you'll find that the denominator in equation 1 actually becomes the likelihood in in the numerator of equation 2. And so it's basically the output of one level of inference becomes the input for the next level. So that's why the denominator, the quantity in the denominator, is also sometimes called marginal likelihood. Because it basically marginalizes over all the parameters of a certain model, and then it becomes the likelihood for the next level. So, and this is equation 2 is a generalization of something like computing a reduced chi-square, because it also takes into account your prior beliefs and any other relevant information. So, yeah, and one good thing about Bayesian inference is Occam's razor. It's also called the law of parsimony, and this is what it says. I think in its original form it says something like entities should not be multiplied without necessity. If you can explain something in the least effortful way possible, you should choose that explanation for that phenomenon. So, and I've heard people misunderstanding Occam's razor in the sense that the simplest explanation is not always the right explanation. The thing is, that's not exactly what it says. What it says is more like this. When two models are equally good at explaining the data, and that's important, you choose the one that's simpler. You don't just choose the simplest model, because obviously the simplest model may not be able to explain all the data. So only when two models are equally good at explaining the data, or more or less equally good based on certain factors, or beyond a certain threshold, you start preferring the one that's more complex. So in simplistic terms, if our model is something as simple as a physical phenomenon, because physical phenomena are often the simplest, because any everyday question from real life would become infinitely more complex than a physical question. So it could be the parameters of some equation that describes a certain physical phenomenon. So it could be the one with fewer parameters. That's what fewer parameters means, simpler in this case. So yeah, so this diagram, what it explains is this. So basically, a model with a lot of parameters can still explain the data very well. And you'll know this from the problem of overfitting. You have, for example, a straight line may be the best model to explain a certain set of data points that you acquire. But if you came up with some kind of polynomial of like, I don't know, like 15th degree or whatever, then that will go through every single point that you collected. So is that the best model that fits the data? Because that fits every data point. And this is the problem of overfitting. And this wouldn't occur if you perform this kind of analysis. Because as you see in this graph, so this H1 and H2 are two different models. And the more complex model will have to spread its predictive power over a large parameter space. While the simpler model wouldn't have to do that. With a certain uncertainty, a straight line may be the best thing that fits it. So you naturally, in the y-axis, you see the evidence will be higher for the simpler model. Of course, beyond a certain point, you will need the complex model. But unless the data really warrant it, you won't have to go for the complex model. You won't have to go for the extra parameters. If you can describe the world with the fewer parameters, it's better to do that, because that's likely to be enough to explain this phenomenon. So yeah, I hope that was a helpful introduction. I think I took too long to do that, but are there any questions? Okay, so I'll move to radio interferometry. So, I mean, you all know this angular resolution thing, right? It's proportional to the wavelength over the diameter of a dish. That's or the diameter of an antenna. And that's like the simple relationship between the wavelength of observation and the size of your telescope. So what you do in interferometry is you synthesize an aperture or an antenna by having two different antennas at two different positions on Earth. And then here, the distance or the projected distance as perpendicular to the incoming wave becomes the diameter. It takes the place of the diameter d in this formula. So what happens here is it becomes lambda over b, which means you can start resolving finer and finer structures on the sky depending on how far you put your two telescopes, right?
Yes, maybe it would be also good to just because some of the students might not be familiar with the resolution concept of resolution. So maybe I would just add that for the to remember that yes, if you have larger d, so here b becomes d, the distance, then the theta becomes smaller, and that means a better resolution. So yes, so because you can see smaller scales, so theta, less the theta, the better the resolution. Just to add for the students, you can go on now.
Yeah. Okay. So yeah, so I think those with a physics background would know this. And also, like, if you look at any radio interferometry paper, they talk about like aperture synthesis and things like that. And why is an antenna called an aperture? The terminology comes from here. So you would know that like the typical like Young's double slit experiment, and there two apertures become the sources of your light. Or like I just took this from Wikipedia, so here it's electrons, but it doesn't make a difference. So and that's why that's how antennas came to be called as apertures. So if you encounter terminologies like this, don't worry about that. It's just that's where it comes from. So, and then what we try to do is, so it's all well and good if we have two different antennas placed at a distance apart to get a better resolution on the sky. But you also need to, so now there's still a difference between just having a dish that large. There's a difference between a dish that's 1 kilometer in size and putting two antennas 1 kilometer away from each other. And that difference, and so this is called like filled and unfilled aperture antennas. So people with engineering background know that. So you try to fill in the aperture or the antenna that was synthesized by using Earth rotation as by using Earth rotation to fill in those things. So this is how it happens. You have two antennas that are located at two different distances, and then so this is something that's generally, we call it the UV plane, but they basically show the projected distance from the origin. Like you don't have to worry too much about that, but you'll see that it starts this plane, that the more this UV plane fills up, the better your data will be. You'll be filling different points within an antenna so that it forms kind of like a complete antenna. So, and for those who know Fourier transform, I should have probably mentioned this. For those who know Fourier transform, the relationship between this plane and the beam of an antenna is a Fourier transform. So I don't know how deep I need to go into that. But
maybe also it would be good to say that the U and V are just in meters or kilometers, so that student can.
Yeah. You can think of it like So let's see how we do this. So there is a simulation tool called ApsinSim, and I have the link here. You can, and I really recommend that you just download it and run it. It's very easy to run, and you will get a more intuitive feeling of radio interferometry. So this,
No, I'll try that. Okay.
So this is what happens. So what you see on the right side is the UV plane. And here, so I just have two antennas here, and then I just take one measurement now, right? And then it gives me 2 points because this is a complex quantity and there is a complex conjugate here, so you don't have to worry about that. So this is all, you just get these 2 points on the UV plane. And you can see that that little thing on the globe, that little light green area, that is what has been measured, like that's the baseline. Now we use Earth's rotation. So after, I don't know, like after a minute or after 2 minutes or whatever it is, you take another measurement. now the antennas have slightly changed, like the positions have changed. So you have covered that bit of that shaded area in the globe. So you'll see that there is a slight increase in the 2 green points on the right. And then after a few more minutes or hours, you'll see that these tracks, these are called tracks, they normally call them UV tracks, and these tracks start getting longer. And now what I do is I'll add more antennas, and then I'll just observe it for a longer time. You'll get something like this. Now this shows that, okay, the antenna that you synthesize is filling up. So the beam of this antenna, or what this antenna can see, will resemble a proper single antenna, a bit more and more. And this is like, you just put it all together, and this is the full window of absence-in. And here you can see that, so there are, what you see on the top left is the very large array. It's a configuration of the VLA, and it's usually, the antennas are in a Y configuration, and they can be moved. So you can fill in different parts in the UV plane. So here it almost feels in a star-like shape, but you can fill in different parts by moving the antennas along this Y farther apart or closer together. So here you see the antennas are in a configuration. Can you see my mouse pointer?
No.
No. Okay.
Because normally people usually see the pointer. Okay, maybe.
Oh, so I don't know what's happening.
Are you using
okay, so I'll just
moving the pointer now? Are you?
Yeah, I am. So
Yeah,
okay, I'll just
in any case,
I'll just explain it. So in the top left, you see the X and Y axis. You see that the offsets are in kilometers. So basically, these antennas are about like 40 kilometers apart in both the X and Y axis, right? And when they are so far away from each other, they will see very fine structures on the sky. So you see the last 2 images, the one that's called model image, and that's one called like dirty image. And I forget why they are called dirty images or whatever. It has to do with calibration. I'll come to that. So if your model image is some cloud or some kind of nebula or something on the sky, when you have antennas so far apart, the resolution, the theta, which is lambda over d, is so fine that you won't be able to see the structure. The sky will look more like what you see in the very last image. It's called the dirty image. So now, if you see, the configuration of the antennas have remained the same, but the X and Y axis have changed. You can just see how they change. The same sky, when you observe with antennas that are closer together, it doesn't have as fine a resolution, so larger structures will be picked out. If you have very fine resolution, smaller structures will be picked out. And you can get a much more intuitive understanding of this. You can just download and run absence-in, change the parameters around, and you'll find that you start understanding the phenomena more. So I'll now move on to calibration imaging. Is there anything you want to ask? Anyone? Okay. Okay, so my field is, sorry, I gave a very long introduction, but my field has to do with calibration and imaging of radio interferometric data. And because you saw that our aperture is unfilled, and there are a lot of gaps in our antenna, this is basically like observing a sky with a big antenna with a lot of holes in it. And this causes a lot of problems. And apart from the problems you face from various things on the sky. So these are different sources of corruption, either the interstellar medium that exists between your object of interest and Earth's atmosphere itself, and the electronics, like things like observing the sky with an antenna with holes. So what we do is we do something called calibration before we make images, radio images from these quantities called visibilities. Sorry, I don't know whether I mentioned it. The quantities that we measure in radio interferometry are called visibilities. Yeah.
So the visibility would be just each pair of antenna measure one visibility, right? So
yeah,
and so with time, number of visibilities would increase for the same pair, and of course, if I have many more pairs, then there will be many more visibilities. Okay.
yeah, and then ideally, you take a Fourier transform of the visibilities, you should get the sky. But because it's not the case, because of all these sources of corruption, you need to do a lot of processing of the visibilities before you get an image that you can recognize or do any science with. So I particularly work on something called very long baseline interferometry. So arrays like the very large array that I showed in the simulation, they are called connected element arrays. So they're all connected together. All the electronics are connected with each other. They all form part of the same observatory. So it's easier. There is something called very long baseline interferometry, which uses antennas and observatories from different parts of the world, which means their electronics are all disconnected. They're all separate. The data are recorded separately, and then they're put together or correlated later, generally. So here is an example of one of the telescopes that I work with. It's called the Event Horizon Telescope, which is a global network of radio telescopes. They have antennas from like in America, in Europe. They even have one in Greenland, which should come alive soon. And then there's one in the South Pole. And obviously the reason for doing this is you get these baselines. The denominator in your lambda over b, the denominator is thousands of kilometers. So the resolution is very fine, b. And that's why I do it, but then there are added problems such as separate electronics. And then of course the atmosphere is different over different stations. You have to account for that as well. So the corruptions that are added to your data are different. It's not the same atmosphere adding the same corruptions over two different antennas. So
one question regarding VLBI, so maybe also for the student. So so in where the antennas, like in the example of VLA, the antennas were all situated in the same place and they were connected with cable, and all the antennas were observing a single object at the same time. But for VLA, for example, at EHT, each antenna can observe during a different time. Is that it, or they still?
No, they try to synchronize it with external clocks.
Okay.
I think there's some ridiculously accurate atomic clocks that are used to synchronize the timestamp.
Although they're in part of the world, they're all observing at the same time.
Yeah, they are observing at the same time, because I mean, even the differences in timestamps could be like very small, but they could still make all the difference if the baselines are very large. Yeah, but they use certain atomic clocks to record the time at which it was exactly observed, depending on the time resolution you want. It could be like seconds, fractions of seconds, whatever. And it's actually usually much smaller than that. And then these times, so now you have different visibilities for different antennas that you can, like different recorded quality, different voltages for different antennas, with timestamps. You bring them all together, bring all the hard disks together. Like for EST, the hard disk from South Pole Telescope, they had to wait for months before they could bring that back from the South Pole, because like the winter, the Antarctic winter, they couldn't go there. So they brought it later, and then using this timestamps, they correlated all the data together. So yeah, so here I'll again give a brief introduction to what is called a measurement equation. This is again that's something I can always explain to you in detail. But these are the different quantities that are involved in measuring a visibility. So there's a quantity called B here is, do you know Stokes parameters?
I think most of the students do not know about that, but yeah,
no.
you can.
Okay,
those are just
So that they describe the.
Maybe you can just say that I is the actual intensity and QV are give us polarizations. That's all we have to.
Yeah, that's all you need to know. So the quantity BS is what that describes the relationship between the intensity and the polarization of the source that you see on the sky. And then you have other quantities, which you don't really have to know what the K, E, and G are, but they are different corruptions that enter the process before you record a visibility between two antennas. So this is the mathematical formalism we'll use. But now we'll just put everything together and we'll see some plots, which I hope, if you're still interested, for 10 more minutes. So
you can go. You can take more time. It's fine.
Okay. Yeah. Sorry, I took so long with the initial.
It was you had to go through the introduction, otherwise people don't understand the later part. Yes.
Okay. So so the one thing is, we talk so much about resolution, but there is, it's not like when your antenna is not very far apart, your resolution is not very fine on the sky, and it's given by the Rayleigh limit, lambda over d, but it still doesn't mean you can't resolve beyond that. And this is where all the stuff we talked about, including a priori information in your analysis, helps. So beyond this limit is called the diffraction limit, and angular resolution beyond this limit can be obtained by introducing prior information about the source, about what you know about the source from previous observations, or based on what kind of source it is. There's a lot of information available, just how to put them together in a quantitative way. And so, not to go into too much detail, theoretically, you can get, theoretically, if you have good enough signal to noise, you can resolve your sources beyond the diffraction limit. And there are some papers that I've cited here. I'll send you the PDF of this. You can look into them. So, and this is one of the things that I tried to do initially. So we did some simulations using an interferometer that's in the Netherlands called WSRT. And here are some details, but all you need to do is look at the diagram. That is the UV plane that I plotted there. So
the
you
X
have
meter.
the X and Y.
Yes.
So now you have something. Well, actually, I don't know whether it's in units
probably
of the wavelength. No, they're in units of wavelength. Yeah. Sorry, I should have put the X and Y labels as well. But anyway, so that's the UV coverage, and we have reasonable signal to noise ratio of 1000:1. That's a good signal to noise ratio, and then we added some noise to it, and this is what we did. So I simulated 3 different sources. And this is one of the first things I did in my PhD. Here, the circle that you see here is the diffraction limit. That basically is given by theta. That's lambda over d. For this interferometer, that's your what is called the point spread function in optics, if you know of the term. So, and then I simulated 3 different source models there. So one is a point source. This is just in the middle, and then one is a slightly extended Gaussian source, and then another is 2 point sources. Now, if you do an imaging in the traditional way, if you remember all that angular resolution stuff we talked about, all you should see is just a blob the size of the circle. You won't really see the structure inside it. By taking into account of, again, the mathematical stuff is in the paper, so it's basically by applying the Bayesian inference, the Bayes theorem, to this data, the data simulated with these models, we were able to pick out these small sources, about 1/5 the size of theta, that we were able to pick out with the simulations. And every time, for every model tested, we were able to pick out the parameters and the location and the strength of each source in this. So this was heartening. So we tried to apply this to some actual near-Bay observations. But this time, we also measured the calibration uncertainties. Let's see how we can do that. So there was this blazar. Just like I say, it's an active galactic nuclei. It's an AGN that they observed. So some people had published something where in optical wavelength, a flare was observed, and immediately there were some follow-up radio observations conducted, but they couldn't see a flare, any extended structure from the radio source. And so this was done using EVN, the European VLBI network that's similar to EST. It has antennas all over the world. And 8 stations participated in this observation, 7 in Europe and 1 in Shanghai. And they saw what was already known, a core that's circular, but they didn't find any sign of extended jet structure, which they expected to see because they saw it in optical wavelengths.
Maybe also
they couldn't see it because,
bit more what you should expect actually from a blazar. So you should be able to see one jet coming out of the supermassive black hole, and the jet is almost in our direction. Yeah. Okay.
Well, at least I mean it's not entirely. If it's entirely face on, then it will still be a circular core, but at least it's not face on. Yeah. So, but yeah, you should be able to see a jet going out at some angle. And they found that one of the problems with their radio observations was that because they had only one station in Shanghai, the atmosphere over that station, and also because it didn't have any other stations closer together, weren't calibrated. There were some electronics errors. They're called gains, antenna gains. There's some electronics errors that prevented them from seeing this. So in our modeling, we were not only modeling the shape of the source, we also modeled antenna-based gains or errors. So this is the image that was in their paper. They didn't see anything. You see that the telescope beam is an ellipse, and all this was an ellipse like the telescope beam. They didn't see any extended structure. And yeah, this is just the UV coverage. And again, so this is what our models comprised of. We had a point source, we had a circular source to see if the jet is face on, and then I have an elliptical Gaussian which will show you a jet that's going out of the source at some angle. So, and the source parameterization is the same for these sources. In addition, we modeled different parameters corresponding to each antenna error and the noise terms. So, and this is the kind of, okay, here at last we come to the kind of plots that we get out of this kind of analysis, which is a relationship between different parameters of the model. So I think this will show it more clearly. So each column here and each row here represents one parameter of the model. So the first column shows the strength of the source, and then like the third and fourth column show its position, and then the structure, the Gaussian, like the major and minor axis, and then the antenna errors. So all you need to take from here is the relationships between different parameters comes out naturally if you do a Bayesian analysis like this. And also, you don't get one value. You don't get, okay, well, I think the intensity of the source is like 4.5 in whatever units you measure. You get an entire distribution for each of your parameters. So basically, your uncertainties come out of such an inference process. So you don't get one value out, you get an entire distribution. So the posterior is also called a posterior distribution. So, and then so we concluded that, okay, once we were able to get the uncertainties on the Shanghai station, we were able to get very clear evidence for, so you see the two red, the two small plots in red, those are the major and minor axes of the Gaussian. So we were able to very clearly show that if you can take into account of the antenna errors, you can see an elongated structure. So yeah.
I sometimes get confused about these plots, so I think it would be good also to, so what, for example, if you could explain a bit more what the shape means of this parameter. So on the x-axis you have the parameters, and y-axis you have the same parameters, and what the
and then each small plot shows the uncertainty in each parameter.
Okay.
Yeah. So if you see on the diagonal, you have like multiple distributions that look like Gaussian distributions. So those are the uncertainty. So for example, normally when you give uncertainties, like for example, you measure a quantity and your value is 1.4, and then you say, well, the value is 1.4 plus or minus 0.2. This is how we give our results, right? And then this is only relevant if your distributions are Gaussian. You see that some distributions here are not Gaussian, so you can't just say 1.4 plus or minus 0.2, because on one side the error will be different, the other side will be very different.
Yes.
So depending on your problem, you'll find that getting the entire shape of how the uncertainties are, like this red area, and how slanted they are, how circular they are, and that is what gives you the relationship between the uncertainties of two different parameters.
So it's kind of a joint uncertainty.
Yeah, it's called the joint probability. Yeah.
Okay.
And you can do it. I mean, you can make a 3D plot of 3 parameters and how their uncertainties play together.
What is actually, like, can you also maybe say like what physically this means, joint probability?
Yeah. So physically, it just means, like, for example, when you see something that's so this is what you can see here. It's the same thing, but then showed in an easier way. What you see as the very slanted dark blue ones show that certain parameters are related to each other. When one increases, the other increases. So these are called the correlation plots that you'll see in statistics, right? So if you have X and Y, and if you have a straight line between them, then you see that they're correlated. When X increases, Y increases.
Yes.
Sometimes the relationship between two model parameters be the opposite direction. So you have this dark red slanted plots where you see, like for example, the first column here is called the S, is the strength of the source. That's the intensity of the source. And you see that as the antenna errors increase, the intensity of the source decreases. It's red and slanted in the opposite direction.
Yeah.
So it gives you, so it gives the relationship between different model parameters naturally.
Mm-hmm.
Either it will bear out the physics or it will confuse you, in which case you have to refine your model.
Mm-hmm.
So that's exactly what happens in these plots. And again, I'm always happy to answer questions on this and give references.
Yep.
So okay, I'll skip this. So now we just looked at some antenna errors, which were called amplitude errors. But the paper that you read, I come to it after an hour. It was about, so because these are all complex valued quantities, it's not just the amplitude, you also have phase variations introduced by antennas, introduced by atmosphere, things like that. And that's essentially what we tried to solve for in that paper. If you understood everything we talked about in the last 1 hour, you'll understand that paper more easily now. So it's basically antenna-based errors in phase that we are trying to model in that paper. So,
Yeah, in any case, it would be also good if you probably say more about that paper in a future meeting. You can do it, like, if you're available.
Sure. Yeah, I'll be very happy to. Yeah. So yes, EST we talked about, and if you remember this black hole image, this is what EST came out with last year, and all these kinds of analysis that I talked about so far, they were done on this image, and so this image is weighted so much that you can trust it. Really, that's the kind of image. Like all this kind of Bayesian analysis, everything was done. Although I wasn't part of that group in this experiment, but this was all done in that. So this is what you see. So you see, your phases shouldn't vary like that, right? Once your visibilities are proper, your phases shouldn't vary. So they should just be the straight black horizontal line that you see. But because of atmospheric errors, phases vary like this, all those colored lines. And this is the variation that we try to correct for using the Bayesian method. So we have something called the delay and a phase And so these are all the different parameters that you would have seen in the paper. And then again, we did something similar. We simulated different kinds of sources, like one Gaussian source and a point source with a secondary source orbiting it, things like that. And then we also modeled this phase uncertainties, and we got plots like this, the one similar to one before. And here you see, because these are simulations, you see that all your diagonal plots are Gaussian. In the real data, it wasn't like that, because real data always has things that we don't know about. Our models haven't taken into account of. Simulations, we know what we put in, but to test our software, these simulations are really useful. So basically the same thing, the shape of the source, strength of the source, and the different phase-related parameters. And you see that the green vertical lines in the diagonal plots are the values we introduced in the simulation. And you see that all these Gaussians, all these green lines fall more or less at the center of the Gaussians, which means our method works. We can get the phase, we can solve for these phase uncertainties. Without these phase uncertainties, you wouldn't be able to get a value on the shape of the source or the strength of the source. That's basically what this shows. And yeah, I'll skip these things. But yeah, I mean, again, for two different point sources, we were able to get like the position of the orbiting source at any time, and also the phase-related parameters. And this I just want to show you. So the green distributions that you see for our model parameters, they are the ones that we obtained with the Bayesian analysis. And you see they're all at 0, which means there are no errors. But the blue and orange are obtained with some other radio interferometry software. We did the same process, but not a Bayesian analysis. And you see that they are centered, those distributions are centered far from 0. Not very far, but still far. So this is the thing, you gain in accuracy and you gain in precision when you add prior information into your analysis. Yeah, but I mean, you can think of many other things here. So you can resolve very complex sources, time variable errors, frequency variable errors, and like you can solve for source like spectral indices, or like can study the polarization properties. And there are many things that you can do with this. Yeah, thanks. I really went overboard with the time, but
No,
yeah, if you're still interested, you can ask me questions.
Yeah, we usually always get a little bit over time, like 10 minutes.
Okay.
This is normal.
Okay. Okay.
Thanks.